Deep beneath our feet, a colossal furnace burns, a hidden power source that has shaped our planet for billions of years. This immense reservoir of heat represents an energy potential almost beyond comprehension. It is the Earth's own internal fire, a constant, unwavering force. We call this phenomenon geothermal energy, quite literally the power of the Earth. It is a renewable resource continuously generated by the planet's core and the decay of radioactive isotopes within its mantle. The question before us is profound. Can this ancient, powerful energy source truly supply all of humanity's ever-growing energy needs? The fundamental source of geothermal energy is the heat stored within the Earth itself. This heat originates from the planet's formation and ongoing radioactive decay. It is a vast, enduring thermal battery. As we delve deeper into the Earth, the temperature consistently rises. This phenomenon is known as the geothermal gradient, typically increasing by about 25 to 30 degrees Celsius for every kilometer of depth. In certain geological hotspots, like volcanic regions, this gradient can be significantly enhanced, reaching 80 to 100 degrees Celsius per kilometer. The mechanism for harnessing this heat is elegantly simple. Water, either naturally occurring or injected, comes into contact with hot rock deep underground. This superheated water or steam is then brought to the surface. There, its energy is used to spin turbines, which in turn drive generators to produce electricity. In essence, a geothermal power plant operates on principles similar to conventional coal or nuclear facilities. However, instead of burning fossil fuels or splitting atoms to create steam, it leverages the Earth's natural clean heat. This makes it a remarkably sustainable and environmentally friendly option. Historically, geothermal energy has been harnessed through conventional hydrothermal systems. These methods rely on naturally occurring reservoirs of hot water or steam found relatively close to the Earth's surface. Wells are drilled directly into these reservoirs and the pressurized fluid is brought up to generate power. While highly reliable and efficient, conventional geothermal is limited by geography. These ideal locations where natural hot water and steam are readily accessible are rare. They are typically found in tectonically active zones with shallow magma chambers. To expand geothermal's reach, engineers developed deep geothermal, also known as enhanced geothermal systems, or EGS. This innovative approach doesn't wait for natural reservoirs, it creates them. EGS involves drilling deep wells, often 5 to 7 kilometers or more, into hot, dry rock formations. Once at depth, fluids are injected under pressure to create or enhance fractures in the rock. This process effectively creates an artificial hot spring, allowing water to circulate through the heated rock and capture its thermal energy. Modern directional drilling techniques, borrowed from the oil and gas industry, are crucial for efficiently targeting these deep, hot zones. The sheer scale of Earth's internal heat storage is staggering. Estimates suggest it holds billions of times more energy than humanity currently consumes. In theory, this immense reservoir could power every home, every industry, and every electric vehicle on the planet. This theoretical potential paints a compelling picture of a future powered entirely by the Earth's core. It suggests a world free from fossil fuels, with a constant, clean energy supply. However, translating this vast potential into practical reality presents significant challenges. The primary limitations lie in the rate and cost of extraction. While the heat is abundant, accessing it efficiently and economically at the scale required for global energy needs is complex. Geothermal reservoirs, while vast, are not infinite in their accessible energy. It is crucial to understand that geothermal reservoirs can be drained if not managed sustainably. They function like a thermal battery that needs careful recharging. Over-extraction can lead to a decline in temperature and pressure, reducing the reservoir's output over time. Achieving universal geothermal power would necessitate an unprecedented engineering effort. We would need to drill tens of thousands, if not hundreds of thousands, of deep wells across the globe. This scale of infrastructure development is a monumental undertaking. The cost of deep drilling remains a significant hurdle. Drilling bits wear out rapidly in extreme temperatures and abrasive rock. Well casings can fail under immense pressure and heat. leading to expensive repairs and delays. These factors drive up the capital expenditure for each geothermal project. Material limitations also pose a substantial challenge. Conventional drilling and well completion materials begin to degrade or fail at temperatures exceeding 400 degrees Celsius. Yet, to unlock the most potent geothermal resources, we need to go even hotter. This pursuit has led to intensive research into superhot geothermal systems. These systems target temperatures well above 400 degrees Celsius, where water exists in a supercritical state. Supercritical fluid carries significantly more energy, potentially 10 times more than conventional hot water or steam. The promise of superhot geothermal is immense. Each well could potentially match the output of a small nuclear reactor, providing a massive amount of clean, baseload power. However, this remains the holy grail of geothermal technology, not yet achieved on a commercial scale. Developing materials and techniques to withstand such extreme conditions is an ongoing frontier of innovation. Currently, geothermal energy faces significant limitations that prevent it from replacing all other energy sources. It is often too costly, too site-specific, and too technically demanding for widespread, immediate global adoption. However, its future role is undeniably critical. Geothermal is poised to become an ultimate baseload partner for renewable grids. Unlike solar or wind, which are intermittent, geothermal power operates 24 hours a day, 7 days a week, independent of sunlight or weather conditions. This constant, reliable output makes it an ideal foundation for a stable energy system. Imagine future cities powered by deep, self-recharging geothermal networks. These systems could provide continuous electricity and heating, creating resilient and sustainable urban environments. Geothermal offers a vision of energy independence rooted in the Earth's own heartbeat. Iceland stands as a shining example of geothermal success. The nation generates nearly 100% of its electricity and heating from a combination of geothermal and hydropower. This remarkable achievement showcases the transformative potential of Earth's heat. Iceland's unique geology plays a crucial role in its success. Situated on the mid-Atlantic ridge, it benefits from a hotspot where magma lies unusually close to the surface. This provides exceptionally high geothermal gradients and easily accessible heat. Other volcanic nations, such as Kenya, Indonesia, and the Philippines, also boast abundant geothermal resources. They are actively developing their geothermal potential, contributing significantly to their national energy mixes. These countries demonstrate that where the geology is favorable, geothermal can be a dominant energy source. For regions like North America, Europe, and South America, which lack Iceland's unique geological advantages, enhanced geothermal systems are essential. EGS technology allows these areas to tap into deeper, less obvious heat sources, expanding geothermal's global footprint. A significant advantage in developing EGS comes from the transferable skills of the oil and gas industry. Engineers with expertise in deep drilling, reservoir management, and fluid injection possess invaluable knowledge directly applicable to geothermal development. This cross-industry collaboration accelerates progress. Geothermal energy, born from the ancient heat of our planet, holds a vital key to humanity's future. It is not merely another renewable energy source. It represents a fundamental component of the planet's own energy system, waiting to be fully understood and harnessed. So, can geothermal energy power the whole world? Theoretically, yes, the energy is there. Practically, not yet. The challenges of extraction rate, cost, and material science are significant. However, these are engineering problems, not fundamental limitations of the resource itself. Our hope for the future lies in our ability to master these challenges. With continued innovation in tools, materials, and drilling technology, we can unlock the Earth's inner fire on a global scale. We are on the cusp of developing the capabilities to tap into this immense, constant power. Imagine a civilization running on the heartbeat of the planet itself. Geothermal energy offers a pathway to a sustainable, resilient, and energy-independent future, powered by the very core of our world. Like, share, and subscribe Pulse Nucleum.